Hi everyone, let's talk more about ionic bonding. In a previous video, we talked about how the metals tend to lose electrons. So Na is sodium, that's a metal. Here it's going to lose this one electron here. Where's my pen? Still working. There we go. Sodium's going to lose this electron, form a cation, something with a positive charge. And chlorine over here is a nonmetal. It's located in the upper right corner of the periodic table. They are elements, the nonmetals, that tend to gain electrons. So we'll transfer. An electron transfer takes place where this electron moves over, chlorine accepts it and becomes an anion, something with a net negative charge. And now opposites attract. Positive cation attracts a negative anion, and we have a new molecule, a new compound, sodium chloride, or table salt. Cool. All right, so that was discussed on previous video. Let's get a little more technical, a little more precise with our language. Let's define two terms. First one is ionization energy. And ionization energy is all about the metal here. It's the amount of energy required to remove an electron from an atom. So we need to make it an ion. So what's the energy it takes to ionize it? We just have to remember that for ionization energy, it usually forms a cation, right? So we're taking away an electron, and the resulting atom then has fewer electrons than protons, or it has more protons. There's a net positive charge afterwards. And this requires an input of energy. And in the laboratory, and in nature, I should say, that energy comes in the form of light. Shine light on the sodium metal. It's actually a metal in pure form. And if you give it the right amount of energy, this electron can absorb the light, and the light held energy, and the energy in the light gets taken on by the electron. I tend to think of it like kinetic energy. So now this electron can go faster and can escape. It can be ejected out of the sodium atom. And you need to input some energy because this electron's bound, held in place, because of the attractive force of the nucleus, which is where all the protons are, and the electron's negatives, opposites attract, right? So you need to input energy in order to get this electron to resist or overcome the pull of the nucleus, the positive charges. So just kind of remember this little slogan, if you will. Ionization energy means you put in energy and out comes an electron. And then we're just going to reverse all that to make anions. So we need a new term to make anions, and the term here is electron affinity. We'll break that down in a second. Electron affinity is defined to be the energy that's released when you add an electron to an atom. So that's the process we did for chlorine. Chlorine was a neutral atom, equal number of protons, electrons, and we gave it another electron, well, the sodium's electron. Chlorine accepted another electron, and it turns out energy comes out when atoms accept additional electrons. Weird. So key ideas here. When we form those anions, let's break, no, you know what I want to do? I want to break down this term a little bit. Where does this term electron affinity comes from? Where does it come from? Affinity is just an old word meaning to like. So if someone has an affinity for someone else, that means I kind of like them romantically. I have a big affinity for chocolate, love chocolate. So that's the term here. So if there's an atom that has an affinity for electrons, yeah, that atom wants to acquire more electrons. And that's where the term originates from. So electron affinity, something that wants more electrons. And so if something wants more electrons and gets those electrons, well, electrons are negative and you get more electrons, that's going to turn the atom into an anion, something with a net negative charge. It's going to have a surplus of electrons, which means it has a surplus of negative charge. Okay, and this is the one that I remember grappling with as a student. I didn't quite get it. I'll see if I can explain it to you now because I finally got it. When you give an atom an electron, energy comes out. Light is actually emitted. And so energy in the form of light actually comes out. When you give it that free electron and it becomes bound to the nucleus. Okay, this is what it did for me. Let's go back up here and through the scribbling, see the electron, and we inputted energy, gave this electron more energy to get out. And so now let's say it just has a lot more kinetic energy. Woo, it's out in space, flying around willy-nilly, all over the place, lots of energy. Yahoo! And now we're saying, hey, crazy little electron, settle down, go stick to chlorine. Oh man. Physically what needs to happen is this electron, if it's going too fast, it'll just ricochet off. And even though these protons are trying to attract it, if it's going too fast, it's not going to be bound. It needs to slow down. It needs to release energy. It needs to become part of the atom. And so that's what needs to happen. So if you take a free electron, it's just going to have a whole bunch of energy. It needed extra energy to get away from the other atoms. And now you need to slow it down. You need to take away some of its energy. How do you take away energy from electron? Well, you ask the electron just to release some light, and light carries away that energy. And now, after the electron releases energy in the form of light, now I can slow down to the point where it can remain stuck to the chlorine atom in this case. Cool. So just remember, electron affinity is the opposite of ionization energy, right? So now we're going to put in an electron, and out will come out energy. Everything's opposites in chemistry, it seems. Positive charge, negative charge, cations, anions. Put in energy, out comes electron for ionization energy. Now we switch it. Put in electron, out comes energy for electron affinity. Cool. That's essentially the whole point of this video. So if you got it, you can run, watch something else, try some homework problems or whatever. But here's a few more things just help us get through chemistry. I'm visual. These help me remember that cations are positive because the word cation starts with the word cat. Cats have paws. Neat little pun there, right? So cations are positively charged. Meow. They're the cutest ion ever. So the word cute starts with a C. That reminds you of a cute cat. Oh yeah, cations, cutest, positively charged. Then we need something to remember the anions, the negatively charged atoms. Well, if you change the A to an O, you got onion. If you cut an onion, they make you cry. And something that makes you cry is negative. It's ruining your day. So onions are bad, they're negative. Anions are negative. Yeah. I tell my students, another way to remember all this is to think about ionization energy. And the sodium wants to kick out an electron. Electrons are negative. So if you kick something negative out of your life, you're more positive, right? So life is better and you get negative things out of your life. So another way to remember. What else I got for you? Let's talk a little bit more in detail about ionization energy. And then we'll look at electron affinity as well. Okay. Here's sodium, here's cesium. We'll take a peek at the periodic table to find where they're at. Turns out they're both alkali metals. Sodium is element number 11 right here. Cesium is element number 55. They're in the same family, a family known as alkali metals. What if I asked you to just give a guess? Which one has greater ionization energy? Which one requires more energy to become a cation? Now, because they belong to the same family, they're going to have the same number of valence electrons, and the column number tells us how many valence electrons, and it's 1. So valence electrons, remember, those are electrons on the surface, or in other words, those are the electrons in the outermost shell. Sodium has 3 shells with electrons. The outermost one is the 3rd shell, and hey, there's only 1 electron in that 3rd shell. Cesium's in the same family, but it actually fills 6 shells. But if you look at the outermost shell, the 6th shell, there is only 1 electron in there. So hey, that's why sodium and cesium belong to the same family. They have similar properties. Their task, their objective is to kick out this one and only electron so they can have complete shells. They can have the same configuration, electron configuration as the noble gases. Why are the noble gases noble? Because they're very, very stable. And it turns out that other atoms with similar electron configurations, meaning same numbers of electrons as noble gases, that makes those atoms stable too. So sodium is like, let's kick out this electron so we have 10 electrons like neon, a noble gas. Or more importantly, all of our remaining shells will be filled with electrons. Cesium's like, yeah, let's kick out that outermost electron so my 5 shells are all filled and I'm nice and stable. Like, what's the counterpart? What's number 54? I think it's xenon. I have to go look at the periodic table, see which element 54 is. It is a noble gas. I think it's xenon. Anyways, shells are full, nice and stable. Back to the question. Which one has, well, let's phrase the question in the sense of which one is easier to form a cation? In that case, which one has a lower ionization energy, right? Because ionization energy means I need to put in energy. I need to shine some light on here. I'm kind of lazy. Nature kind of likes the path of least resistance too. Which one's easier to form a cation? Which one has lower ionization energy? Well, one way to answer this is try to compare apples with apples, meaning that sodium has 3 shells, cesium has 6. So let's put 6 shells around sodium. So they have equal number of shells. Now, is that breaking any rules? No. Remember, shells are just empty areas, volumes of space. It's just a place where you can put electrons. Sodium doesn't have enough electrons to fill the 4th, 5th, or 6th shell, but they're still there. They're just regions of space. I think of electrons filling orbitals, and those orbitals are just regions of space, or like parking lots. Or if these little electrons are like airplanes or satellites in orbit, the shells are really just flight patterns. If you watch the electrons, where are they hanging out? Well, this 3rd electron is in the 3rd shell. It's hanging out in a circular spherical volume of space. Its flight pattern is like within this ball of space. And if you go out farther, there's a larger sphere of space. We call it the 4th shell, but in sodium it's empty. So you can put as many shells as you want. Sodium's not going to put any electrons in it, but they're still there. Okay, that helps me understand the concept of ionization a little bit better. And now I can make a comparison. Which one requires more ionization energy? I can go to the 6th shell and just yank this outermost electron pretty easily. But if I go to sodium, I need to yank once to get it up to the 6th shell. And then I need to yank it again, this energy being the same as this energy, maybe. So yeah, sodium's going to require more energy, a larger ionization energy. And I think I originally phrased the question, which one has lower ionization energy? That would be cesium. Can I abbreviate ionization energy as EI, meaning it's easier to make a cation? Meow. A positively charged atom. Yeah, so that's the answer. You have more shells to overcome, a greater distance. What else can we do here? Each shell has a different amount of energy. We discussed that in the previous video. The lowest shells have the lowest energy. As you go up in shells, the electrons need more and more energy to get into those higher shells. It's not 100% accurate, but if you think of electrons as particles, and that's where the inaccuracy comes in, it may be that electrons behave more like waves inside atoms. But let's pretend they're completely particles. And if you're an electron in that first orbit, it's going pretty slow. You need to go faster to get to the second orbit. You need to go faster to get to the third. The analogy I like to run through my head is, what if the nucleus is planet Earth, and I just sprint across the surface, and then I jump in the air? How high do I get? Well, not very high. Well, now I get on a motorcycle and rev it up, go as fast as I can, I go off a ramp, and now I can get even higher because I have more kinetic energy. What if I get an airplane, just take off? Now I can fly up even higher kinetic energy. Finally get on a rocket ship, and now I can go as high as I want. The rocket ship has the greatest kinetic energy. So to get up really high, you need to go really fast, higher shells, more energy. Okay, now with that analogy, for me, hopefully for you too, it's easier to make the comparison. Who's easier to remove, this electron in sodium or this electron in cesium? Well, cesium's electron's already going really fast. It's already really, really high. Give it a little more energy to completely knock it out of the atom. Sodium, you're going to need to get enough energy to get it up to the 6th shell and then beyond. It's going to require more energy. It's going to take more ionization energy. It's more work. Just use cesium if you're given a choice. Cool. Oh, before I move on, sorry, one more idea, especially those of you who are going to take more chemistry later and go even more in depth into this. You might say, wait a second, Dennis. Okay, I accept your idea about the shell energies being higher as you go up, but what about the positive charge? Sodium is element 11. There's 11 pluses in the nucleus. But cesium is element 55. There's 5 times as many protons, 55 pluses in here. So isn't this electron being pulled back by more protons and held more tightly? 55 pluses against this measly electron compared to only 11 pluses in this electron? Well, it's true. There are more positive charges, but there's also more negative charges in cesium. So cesium is element number 55. The neutral atom comes in with 55 protons, but it also comes in with 55 electrons. The 55th electron is farthest away. That's the valence electron. The other 54 are core electrons, and they're lower, below this outermost electron. And electrons repel electrons, so these 54 electrons actually are all pushing this electron out. 55 protons are yanking this electron back in. So you have 55 pluses trying to draw the electron in. You have 54 minuses repelling the electron out. Your net difference is a +1. This is called the effective nuclear charge. All the electrons below the electron you're interested in are kind of being subtracted from the nucleus to give it an effective nuclear charge. And now if the effective nuclear charge of the outermost electron is only +1, that's the effective nuclear charge for the outermost electron in sodium too, right? There's 10 core electrons all below the level, the orbit, sorry, the shell, the orbital, if you will, of the last electron. These 10 electrons are repelling it out. 11 protons are attracting in. The next net difference, the effective nuclear charge, is also +1. So essentially, the net attractive force of this outermost electron is +1 for both cesium and sodium. And then you could argue that, wait, if they're both having the same effective nuclear charge, this outermost electron's farther away, and electrostatic forces get stronger as you get closer, and they weaken as you get farther away. So the charge is +1 in both cases, but this 6s electron of cesium is farther away, and so its attractive force is weaker than the 3s electron of sodium. So there you go. Another case for saying cesium's got the lower ionization energy. What's the other case? Well, that's electron affinity. The atom has an affinity, an attraction for that extra electron. We're going to form an anion. So I might ask, okay, well, let's think about this. I want to take the lazy way out. I want to make an anion easily. So that means throw an electron at one atom, throw an electron at the other. Who likes to make the anion the best? Well, the one in both cases, energy is going to come out. So we're going to put in an electron, and out will come light or energy. So the one that makes the anion the best is the one that can release the greatest amount of energy. So now we're looking at the highest electron affinity. Again, opposites, right? For ionization energy, we had to do the work. We had to supply energy to yank the electron out. So what's the lowest amount of work it can do? What's the lowest ionization energy to make a cation? Here I'm like, give me something. Give me some energy. Ooh, what's the maximum amount of energy you can give me? Here's an electron. Give me some energy. What's the highest electron affinity you can give me to make an anion? Okay, so that's the question. And let's go to the same family. I'm going to go to column 7. These are the halides or halogens. And I got chlorine over here, element 17, versus acetine. So I found this on the web. I thought, cool, lots of electrons already drawn for me. So I'll just use that element. This one's radioactive, so I will avoid this in the lab. But this isn't radioactive on the page, so I'm good. 85 electrons, 85 protons. They are all halides, same family. What's going on? What's special with them? They all have 7 valence electrons. 7 electrons on the surface. So I got 1, 2, 3, 4, 5, 6, 7. Good. Chlorine, 1, 2, 3, 4, 5, 6, 7. Nice. They look the same from the surface. 7 electrons on the surface. That gives them similar properties. They behave similarly in the lab. And one of the properties is we want one more electron so we can look like a noble gas. Our chlorine wants to look like argon with 18 electrons. Acetine wants one more electron so it can look like radon. Another radioactive element. Interesting. But 8 is the name of the game here. Give me another electron is what these 2 elements are saying. And now my question is, who wants it more? Who's going to give you more energy? I got the electron. Who wants it more? Well, compare apples to apples. Let's add extra shells to chlorine. So they both atoms. Now we see all 6 shells. I give acetine the electron and boop, here you go. It just filled the 6th shell. We're in the P block. So actually this extra electron I just gave acetine is a 6p electron. And I say, here, chlorine, here's an electron. I'll put it in the 6th shell. Give me some energy. It gives me some. Just like acetine gave me some energy, getting this extra electron. But now this 6th shell, the electron says, whoa, I need to go down to the 3rd. And to slow down even more, to go down even to a lower level, it needs to give out more energy. So chlorine has a higher electron affinity because that electron gets buried deeper into the atom. And the closer it gets to the nucleus, the more stable it becomes. It's slower, the lower the energy. And there's more, and remember we had that free electron like flying all over the place, woo! And we had to slow it down to make it stick or bind to the atom. And so as I slow down this electron to the 6th shell, get some energy. But I take that same energetic electron, slow it down all the way down to the 3rd shell. Wow, we really have to slow it down. You need to remove a lot of energy. So chlorine has a higher electron affinity. Nice. Okay, let's leave and end this video with a couple ideas. A little summary down here, but also this main idea. If you go to a table of ionization energies and a table of electron affinities, right? Because scientists love quantifying things and giving exact numbers of things as best they can. You'll see that the numbers are written as negative values for electron affinity. Okay, and that's just reflecting the fact that energy is being released when you donate an electron to an atom to make the anion, right? Energy can come out, you get it, it's being released. So the negative sign just means energy comes out, not ionization energy, we have to do work to yank that electron out. You have to put in energy, that's a positive amount of work. Give the electron electron affinity, out will come energy for you. And in another sense, the electron used to be really energetic, now it slows down. Its energy decreases. That's another reason why the electron affinity is also decreasing its negative. Cool. Enough about that. And then just remember, if there's a homework problem that says pick the atom with the lower ionization energy, that's just fancy talk for saying which atom makes a better cation, which makes it easier. And on the other hand, opposite is opposite. Lower ionization energy, but higher electron affinity is going to mean which atom is going to make the anion more easily. Cool. That's all for now. Have a good one.